All right, let's dive straight into this explainer. I am absolutely pumped to tackle this topic with you today because honestly, we're looking at the ultimate test in modern networking and security. We're talking about protecting decentralized physical infrastructure from cyber attacks. It's one thing to protect a database, right? But it is an entirely different beast to secure systems that literally interact with the physical world around us. So let's get right into it with some bright, focused energy, because the stakes literally could not be higher. So here's the million-dollar question. How on earth do we protect decentralized systems from cyber attacks in just milliseconds? Picture a massive smart grid, or an automated water treatment plant, or even those connected autonomous vehicles we're seeing everywhere. In these environments, an attack happens in the blink of an eye. If your go-to security protocol involves sending traffic logs all the way to some distant cloud data center, waiting for an AI to crunch the numbers, and then waiting again for a response to travel back over the network, well, that takes way, way too long. That latency, it leads to catastrophic delays. We absolutely have to find a way to defend these systems right there, exactly where the action is happening.
And the stakes here, they couldn't be more different. Think about it. A traditional web server hack usually just means digital data loss. Bad, sure. But a compromised cyber physical system, what we call a CPS, that means actual physical destruction. We're talking machinery breaking down, power grids going dark, and terrifyingly, human lives being directly put at risk. We are bridging the digital world with the physical world here, and that means a digital breach can and will cause catastrophic physical damage.
Okay, so here's our roadmap for this explainer. First, the cyber-physical threat. Next, why the cloud fails. Then we'll look at the Edge ML pipeline, shrinking the AI, federated learning, and finally wrap up with cloud versus edge security. It's a nice logical progression from the high-stakes problem right down to the micro-level engineering solutions. All right, section 1, the cyber-physical threat. Let's map out exactly what kind of attacks we're dealing with. Before we can even think about building a machine learning defense, we really have to understand the specific threats facing this physical architecture on the front lines. Take sensor spoofing and data injection. Just imagine an attacker tampering with physical sensor readings, tricking a nuclear reactor cooling pump into reporting that temperatures are totally stable, when in reality, the whole system is overheating. Yikes, right? Then there's distributed denial of service, or DDoS. This is where botnets hijack thousands of weak little IoT devices just to flood local fog gateways, dropping legitimate critical control traffic in the process. And finally, we have man-in-the-middle and replay attacks. This involves intercepting industrial traffic and basically playing back valid command sequences to manipulate physical actuators completely without authorization. Moving right along to section 2, why the cloud fails. Let's talk latency and outdated methods. So, you might be wondering why traditional centralized security completely falls apart against these real-time physical threats. Well, take signature-based detection. It's old school, it relies on known attack patterns. But in the wild west of IoT environments, attackers are constantly throwing novel packet mutations and zero-day exploits at us. You just can't rely on known signatures when you're looking for a footprint that literally hasn't even been made yet. It's totally useless here. Because of that, we desperately need a paradigm shift over to anomaly-based detection. Instead of searching for known bad behavior, we use machine learning to train models on what normal operational behavior actually looks like. Once you know normal, any sudden deviation acts like a massive red flag, triggering an immediate safety response. But hey, remember that latency problem we talked about earlier? Yeah, we can't do this in the cloud. We absolutely have to run this machine learning right at the edge to catch these unseen deviations in real time, exactly where the device sits. Which brings us to section 3, the Edge ML pipeline. Let's see how this on-device security actually works. To really visualize this line of defense, let's sketch out the architecture block diagrams step by step. First up, raw sensor telemetry, stuff like pressure or voltage, and network packets hit the data ingestion buffer. Now, we obviously can't feed raw, chaotic, high-frequency data straight into an AI, right? So it moves to feature extraction. We use a sliding time window here to capture nice structured features, like temperature drift. Those processed features are then instantly fed into on-device inference. This is where we utilize super lightweight engines like TensorFlow Lite running natively right there on the device, before reaching our final step, the anomaly evaluator. Let's zoom in on that final evaluation step. The inference engine acts kind of like a judge, computing an anomaly score based on its reconstructed baseline of normal behavior. Basically, when the observed input strays a bit too far from that baseline, the score goes up. The very moment that score exceeds our predefined threshold, boom, the local actuator immediately isolates the compromised sensor or drops the malicious packet in sub-millisecond time. No waiting on the cloud, no asking for permission, it acts instantly to save the system.
All right, section 4, shrinking the AI. This is where we get into model optimization. Now, we face a pretty profound engineering challenge here. I mean, how exactly do we fit a massive, resource-hungry neural network brain onto a tiny, super low-power edge microcontroller? Well, to make this magic happen, engineers rely on 3 brilliant compression techniques. First, quantization, which basically reduces the precision of the numbers the AI uses to compute. Second is pruning. This is where we identify and snip away zero or near zero weight connections in the neural network that aren't really doing anything anyway. That leaves us with a beautifully sparse, lightweight model. And third, knowledge distillation. This is super cool. It's where you train a massive, highly accurate teacher model up in the cloud and then essentially transfer its knowledge down to a compact student model that is small enough to run natively right on the edge.
Let's look a little closer at quantization, for example. By dropping the model's weights from big, complex 32-bit floating points down to simple 8-bit integers, we managed to slash the memory footprint by an astounding 75%. And the absolute best part, doing this results in virtually zero loss in detection accuracy. So we're drastically shrinking the brain, but it stays exactly as smart at catching those cyber threats. It's a real game changer.
Next up, section 5, federated learning. How do we keep these edge models updated?
So now we have all these tiny, highly efficient brains distributed across thousands of physical devices, right? But they still need to learn from new threats. The problem is, sending raw, sensitive operational data back to a central cloud to retrain an ML model is a massive privacy and security risk. We just can't do it. The clever solution here is federated learning. Instead of moving the data, the edge devices train the model locally, using their own private information. Then, they transmit only the updated model weights back to the cloud. The cloud securely aggregates all these tiny little weight updates into one global master model, and then safely distributes the newly improved defense capabilities back out to all the edge nodes.
And finally, section 6, cloud versus edge security, the ultimate comparison cheat sheet.
Bringing this all together, the contrast between the old way and the new way is honestly pretty stark. Cloud-centric security relies on signatures, it suffers from terrible latency over long networks, it constantly exposes your data, and worst of all, it completely fails if the network goes down. Edge ML completely flips this paradigm. It detects 0 days via anomaly detection. It responds in under a millisecond, locally. It fiercely preserves privacy through federated learning, and most importantly, it continues defending that physical machinery completely autonomously. Even if the device goes completely offline, it is still fully protected.
As we wrap up, I really want to leave you with this provocative thought to chew on. As edge devices keep getting smarter and these compression techniques get even more advanced, will autonomous edge AI eventually cut the cloud out of security entirely? The arms race between physical IoT devices and cyber threats is moving incredibly fast, and it is constantly pushing the boundaries of what these tiny microcontrollers can actually achieve. It is such a fascinating frontier. I really hope this explainer gave you a solid, structured understanding of exactly how we are defending the physical world today. Keep exploring, stay curious, and hey, thanks for learning with me.